13 has always been a lucky number for me. I married my wife on August 13th, 2000, and we are still married. She is with our kids now, both of whom are under the age of 13, keeping them occupied and out of my hair. So I would like to express words of appreciation to her, and I would also like us all to give a bit of acknowledgement to all the people who are not in this room, making it possible for all of us to be in this room having such a great time. So let me start by reminding you how base 3 works. In base 3, the digit sequence 102 represents the number 1 times 3 squared plus 0 times 3 to the 1 plus 2 times 3 to the 0, which makes 11. In base 2, 102 doesn't mean anything because you're not allowed to use the digit 2 in binary, but let's allow it. Extended base 2, 102 represents the number 1 times 2 squared plus 0 times 2 to the 1 plus 2 times 2 to the 0, which makes 6. So now I ask, could there be a sequence of zeros, ones, and twos that represents the same number in both base 2, extended, and base 3? That is, can you count in base 2 and 3? The answer is yes. Single-digit numbers, 0 by itself, 1 by itself, 2 by itself. That's stupid. No, you can't. Because a sequence of 2 or more digits in the set 0, 1, 2 has larger value in base 3 than in base 2. So you cannot do it, except you can. Here's 11.222 dot, 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 an infinite expansion going off to the right, which, interpreted in base 2 or base 3, has the value 5. How did I find this? By a generalization of the carrying procedure where you change a digit and not only modify the digit to its left, but also the digit to its right. And I'm going to allow temporary digits, 3, 4, 5, and 6. So let me describe the rule for carrying, show you a slide about why it works, and then apply it to solve that problem. So the carry rule is if you have an expansion that has 3 consecutive digits, in which the middle one is 5 or larger, you can reduce that one by 5 as long as you increase the digit to its left by 1 and increase the digit to its right by 6. And if you do this, you will not change the base 2 or base 3 value of your expansion. We call this operation firing or explosion. So why does this work? You can skip this slide if you're not a mathematician, but if r equals 2 or r equals 3, then r minus 2 times r minus 3 equals 0, and that implies that 5 times r to the k equals 1 times r to the k plus 1, plus 6 times r to the k minus 1 for all k. But let's just do it. So let's apply the carry rule repeatedly to find a base 2 and 3 representation for the number 5. So we're going to start with this temporary representation that's illegal because we're not allowed to use a 5. So we're going to reduce that digit by 5, increasing the digit to its left by 1, and increasing the digit to its right by 6. Do you see a problem here? Yeah, not allowed to use 6. No 6 allowed in these talks. So reduce it by 5, increase to the left, increase by 6 to the right. Do you see a problem here? It's going to keep happening over and over again. But there's a pattern to the way it keeps happening over and over again. Each position only fires once, and after infinitely many firings have happened, we're left with 11.2222 dot, 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 which does indeed add up to 5 in base 2 or base 3. Now, this explosion procedure lets us get rid of any digit that's 5 or greater, so let's allow any digit from 0 to 4. And we'll use this expanded digit set to count onward from 5 all the way up to 13. Let's try it. 11.2222. Let's increase the units digit by 1. That represents the number 6 simultaneously in base 2 and 3. This represents the number 7. This represents the number 8. If I add 1 to the units digit again, I get 15.2222 dot, 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 which I'm not allowed to do, but perform infinitely many firings, and we get 21.4444 dot, 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 which represents 9, and onward to 10, 11, and 12. And when we add now 1 to the units place, again, we get a problem, 25.4444. But after a huge amount of firing, we're left with 32.4444 dot, dot, dot. So can you count in base 2 and 3? Yes, you can, but no, you can't. Does 32.4444 dot, dot, dot really equal 13 in base 2 and 3? If you add this infinite series, when you plug in the base r equals 3, it does evaluate to 13, but it evaluates to only 12 when r equals 2. What is causing this arithmetical vanish? Ask me if you want to know more. 4 final remarks. First, in the abstract, I mentioned base 1 and 2. I don't have time to talk about it, but can you figure out what it is? 2. Can you count in base 2 and 3? Yes, you can. After all, Stephen Lucas found a version of base 2 and 3 that lets you count as high as you like, using now the digits -1, 0, 1, 2, and 3. For instance, 13 in this base is written as -1, 3, 4, 1. Challenge for you, find the right way to do the carries. 3, if you like funky bases, check out the essay on base 3 halves at the website for my monthly mathematical enchantments essays, essay number 27. Finally, check out James Tanton's exploding dots approach to representing numbers, which makes these sorts of games very visual and appealing. And check out the Global Math Project, which in the past year has brought exploding dots to over 4 million kids all over the world. That's all I got. Thanks for listening.